So today, we're going to talk about how research, the type of things that research at the foundation has been cooking over the last year or so, and things to come. Right. All right, so the type of things that I'm going to talk about are actually things that are not in production. Maybe will actually never be in production, or at least in the mainnet. Those might be applications that we'll see in other contexts. And in general, this is really about results that we're looking to benefit from in the short to medium term. So I'm not talking about things that will be like 5 years out, but more like in the 1-2 years time frame max. And in particular, the type of things that we're looking into are around performance and scalability in general. And the reason for that is that, well, on that front, we actually always need more. Actually, as I unpack the type of things here around like what does scalability and performance really means, it's actually a lot more than just TPS. Those type of things are actually very scenario dependent. So maybe like certain things that you do might change, let's say, latency, and maybe you get like something out of that, right? But like it could also be like other things that the network does for you. And also in the context of research, we are actually looking into potentially like ideas that are mutually exclusive, and that's actually totally fine. Like the reason we have to do that is we don't know yet like how far those type of things can go, and in particular, going back to the use cases, depending on how things kind of evolve, like we want to kind of have like better options, right, on that front. And then finally, some of those results are actually coming from the Groundhog team that, so David yesterday presented some interesting things there, where the team is answering a quite different type of question that is really around like what happens when you go beyond the million TPS type of numbers. And okay, so, and talking about more TPS, there are a few strategies that we can employ on that front. So like for the ones that just joined, Marta just talked about the one way to increase performance, and that's around getting rid of idle time, meaning when nothing is really happening with your resources. And a quick recap there is like a way to think about it is you have several phases of, as the ledger is closing ledgers, where you need to reach consensus, and then from that result, you end up applying that ledger. And if you look at specific resource types, consensus is actually mostly bandwidth, meaning like data being exchanged over the network. And then applying a ledger is, in this example, I'm looking at CPU, is basically where we do the actual work. And what you can observe on this graph overlaid there is that those are actually off phase. When we are doing consensus, we are using the bandwidth, but we're actually not doing anything else really with CPU, and then vice versa during ledger application. And just by looking at that, you already see that at most you're going to use like 50% of your resources available. So it's kind of already you're leaving on the table half of your capacity. And the solution there is to just do things in parallel. And by doing that, you're actually one step closer to being able to utilize 100% of those resources, which is obviously like better, twice as much as. All right, there are actually other ways to get more TPS, and it's just to do more things per unit of time. So like one of the strategies that we are looking to, and we're actually pretty far into this investigation at this point, is adopting a just-in-time execution for soroban contracts. This brings performance to like within an order of magnitude from native performance, meaning that right now, if you run a soroban smart contract, you have about like 100x slowdown compared to native. So this will bring it to within like, within 10 basically. And other ways to increase performance per unit of time are on increasing parallelism. And then there you have like actually two ways to do it. Like one is to scale up, meaning buying better hardware. So you have like more threads and so on. The thing with this particular strategy is that it works actually fairly well at the very beginning as you start to scale. But at some point, you're going to meet some diminishing rate of return, right? Like at some point, it becomes extremely expensive to gain a little bit more capacity. And then you have like the laws of physics at some point also. So that's where in terms of curve, cost to performance, you now have to look at more like scaling out strategies. And this is where you can get like in the multi-million type of numbers. And the real question that we're asking in that context is what happens if operators are more sophisticated than they are today? On those last two topics, right, where we increase parallelism, like the question is really also a lot around governance and the type of changes that we're willing to make in the broader ecosystem. So yeah, this is not just like you can stamp your fingers and then suddenly you have like those type of numbers. All right, so now let's move to other strategies that we've been looking into on improving performance, and in particular around how earlier I was talking about the type of resources that we have on the network. And one of very important and fairly scarce resource is actually the network capacity, like as in bandwidth and things like that. Because this is how everything moves on the network. And I'm going to use over the next few slides the same kind of toy little network that is how nodes are connected over the network. And I'll start by describing like the current strategy of how data moves on the network, which is called flooding. So flooding is actually a very simple way to propagate data over the network. When a node is receiving information, it's going to just forward it to all the other nodes it's connected to. So while this is first of all, very simple and resilient in particular to censorship, it's also extremely wasteful. So I have like a few examples of amplifications that can happen with this type of strategy here. The first one is around like the thing I was saying, like you receive one message and you forward it to all the other nodes you're connected to. By doing that, this orange solid node in the middle is actually seeing or suffering, I guess, a 7x amplification on the bandwidth point of view, which if you think about like the network links, this may cause actually those nodes to reach their link capacity. So it's not great. And then another type of amplification that can happen is through duplication of traffic. And this is something you can see with the blue path, where you have like race conditions to reach the same node. And yeah, there's actually not a whole lot that this node can do. It's just going to receive the same data several times. All right, another thing that to really kind of think about is how data is getting relayed on the network. So the impact of relay can be fairly important depending on the type of things the type of messages that we are propagating, right? So for consensus, we need validators to be communicating with each other as efficiently as possible. In this particular example, what you can see is that for those validators to actually exchange all messages, every time they are going to have at those 3 hops in terms of relaying. And then another type of things that you need to do and propagate on the network are the transactions themselves. That when you submit a transaction to the network, what needs to happen is that those transactions need to reach the validators so that they can be included in a block. And same thing there, it can be potentially fairly wasteful because you end up propagating transactions everywhere. Let's see. So now, building on what I was saying, then the question is like, how can we really make this better? And for example, like just talking about bandwidth. Bandwidth, like I was saying earlier, is one of the extremely scarce resource types. And what we're going to get by reducing bandwidth utilization is, well, we can do something with that extra capacity. So either you can just shove more transactions or more useful data, right, in the same amount of bandwidth that you have. So that means more TPS. Or you can also just leverage the fact that now, if you have less data to transmit, you can lower latency. So it's a choice that you have to make. Those are an example of like mutually exclusive type of things. Like you can't do both. And on the where you want the data to go, if you think about transaction queues, like I was saying earlier, the goal is really to reach validators and avoid propagating data that would just go to nodes that are not validators on the network. And then for consensus, here you have like actually two interesting like categories of consensus messages. You have like the phase when you're trying to reach consensus. So for that, you're actually looking at validators, exchanging those messages as efficiently as possible. And when consensus is reached, you want to propagate now this information on what the block is about to the rest of the network. So those are like things to keep in mind as we progress into solutions. So now, as far as like interesting ways to take advantage of what I was saying earlier, we are looking to structural overlays. So structural overlays give you a new superpower. You can now, as a originator of some piece of information, let's say a transaction, you can decide on what should be the destination. Earlier I said transactions need to reach validators and nothing else. Well, we can do exactly that in a fairly optimal way with a minimal redundancy. In this case, the example I put is I want at least or exactly two alternate paths. That's for just redundancy. And I want to reach all three validators in that network. And I can do the same actually with transactions, with consensus messages. With consensus messages, we can actually do something else. We can have like a layered architecture where, going back to what I was saying earlier, during consensus, you can have like this inner kernel that you have on the screen with validators exchanging messages, and then post-consensus, meaning when you have the result of a SCP, you can actually now propagate the information outwards. You can think of that as like rings in a network, where now you can actually use the capacity from a ring to go out to make the data propagate even more efficiently. And then another strategy that we are looking at employing is erasure codes. So erasure codes are just a fairly simple way to kind of ring code data. So the naive way that you would think of forwarding data, like earlier I said, a node receives information and is going to forward it to a bunch of other nodes. Well, the naive way would be to just send the same data, like in this example, 5 times over. A different strategy that can be employed is to encode the data in a slightly larger payload, split that data into unique chunks, and then have each of those unique chunks sent to different destination nodes, and then themselves they will forward that information to the remaining nodes. The thing is that when you do that, you actually end up distributing the network utilization across all nodes. So this is actually a very good way to, in a way, bypass some of the limitations of network links. Because in the first example, right, like what happens is that if you have, like, let's say, a 10 gigabit network interface, well, by using a multiplier of like 5, I can really use a fifth of this capacity. Whereas in this Azure code work, well, you're now going to actually use almost the entire capacity that you have. Let's see. So until now, I was talking about overlay. So this is transport. Transport is impacting everything. There are other ways to actually make improvements to this stack, and to basically like think about like higher levels. So like if we can make improvements to consensus, it's going to, I mean, consensus itself will benefit from those transport improvements. But if we can make improvements at the consensus layer, well, now we can potentially even benefit even more from those advancements. Even in current world, like as in like those are like they benefit from each other, but you don't have to do one and then the other. All right, so like a quick recap, I guess, on what consensus really needs. You need to propagate blocks, so those are like the transaction sets that are included in a ledger. And then all validators will have to exchange 6 messages as part of agreement. And the two things that are really impacting consensus performance are going to be about how much bandwidth do you really ask for transport, and then the latency, between all those validators. So one of the things we're actually looking at doing is changing the way block itself is propagating. So like right now, the way this works is when you have like messages getting propagated over the network, they are connected in a way to the block itself by reference. So the very first message that a validator sends will have like this pointer, basically. And then when a node receives that very first message, it will see that the hash that is being referenced is something that it doesn't know about. So it's going to ask for the originating node for that particular piece of information. And as that first message keeps getting propagated over the network, the same thing is going to happen. The second message, in this example, message B, is going to actually go very much faster because now you do have the pre-image. And then there, like to make things better, what we actually end up doing is delaying when do we actually need that pre-image. And by doing that, we are now like for like the first few messages of SCP, we can actually already we don't need to block basically, right? So we are going to have in this particular example, the message B will reach will have propagated over this quorum in half the time that it takes for compared to the previous example. Let's see. Another thing that we're looking into is around leader election. So here we have to go back to how SCP actually functions. So we have like two distinct phases of SCP. One is called the nomination protocol, and then after that you have the ballot protocol. Nomination is its purpose is to produce candidate blocks, basically, that the network can agree on. And then the ballot protocol is the one that ensures that only one of those blocks will be the one that everybody agrees on. Now, the type of the problem that we have here is that all this process takes about 6 messages. And then the other problem that we have is that there is actually a fairly high chance of timeouts with conflicting leaders when you end up with fairly large quorums with asymmetrical structures. So in SCP, what happens is that you have like a trust of graph between nodes. Who do you trust, right? And over time, not everybody may trust the same entities, right? And when some drift, which is natural in this kind of system, happens, the current implementation will actually time out. Oh, already? Okay. All right, so we made it better, I guess, by separating those processes and by making the slow process be out of band from the rest. And thanks to that, we now have a latency that's really driven by the fastest quorum, bandwidth reduction over a 10x quite easily, and a path towards sub-second latency. So the next steps are going to be to prototype this further, and then graduate the things that we think make sense to production. And I'm also very happy to say that we are in the process of hiring a director of research that will allow us over time to expand research beyond only scalability and in other topics that are very important for the network. Thank you.